All right, hello again. So earlier today I talked about after Exascale. So what are some of the things we're hearing from customers and thinking about as we look at the Exascale? Now I'm going to talk about actually what we can do with Exascale and some of the technology that we're making available over the next couple of years or so. And a lot of this, again, is creating the latest compute solutions for the digital economy. So first off, we're very privileged at HewlettPackard Enterprise to be working on the first 3 Exascale machines for the United States. But it's not so much the systems themselves, but it's really some of the new technology that we're bringing out that we hope to be able to create a broad use for as we go forward. So from our standpoint, it's not just about a single Exascale machine, but it's about a new era that's now coming before us. And so this era is actually being driven through digital transformation. So it's that massive amount of data that's out there from our connected devices, from our Internet of Things, from all the sensors out there, from the systems that are able to generate large amounts of simulation data. There's also larger models now, so greater fidelity given the processing capability of the systems now can actually get more accurate models, get more accurate weather models, get more accurate finite element models for computer data engineering, for example. And of course, new algorithms, AI, ML, variety of new workloads that are coming out and becoming available in this time frame. And so from our perspective, the Exascale era is a combination of big data analytics, artificial intelligence, and modeling and simulation. So modeling and simulation, of course, is the traditional HPC workload. When we talk about HPC in the past, it's really been trying to model or simulate the real world. Now, with all these sensors, we can actually measure the real world and actually feed some of that data into our simulation and get a more accurate simulation, a simulation that converges faster. We saw earlier on our talk with the autonomous aircraft that was some of the work they were doing as well. And of course, when we combine big data analytics with all those different simulation data that we have, we can actually get interesting new insights into that data that perhaps weren't available before. So I think Mark Parsons of the Edinburgh Parallel Computing Center probably said it well. And Exascale is not so much about doing an exaflop by itself, but it's actually bringing out the capability that allows us to do better scientific industrial research. And so one of the things we decided to do as we developed these new Exascale machines was to develop supercomputers that perform like a traditional supercomputer with very great power, very low latency interconnect, lots of memory capability, lots of storage capability. But we also wanted to have a lot of the look and feel of a cloud environment. So in terms of the multi-tenancy, the flexibility, and the enjoyment of heterogeneity that's available in a lot of cloud applications. So again, our goal is to be able to take that Exascale technology from every data center, from Exascale to as a service. And so you always worry about whether this next frontier of high-performance computing will be interesting broadly across the market. After all, is there a need for an exaflop in a lot of industrial applications, for example? And we'll say categorically, yes. We've talked to a lot of customers in a lot of different industries. And as HewlettPackard Enterprise, we have a lot of industrial customers. In fact, our commercial HPC business is as big and as vibrant as our public sector business that we're doing. And here's a quote from Mark Miley from Procter & Gamble. And Procter & Gamble is one of the largest consumer products companies in the world. So shampoo and soap and laundry detergent and household goods and Pringles potato chips, these are things that Procter & Gamble does. And so Mark Miley at Procter & Gamble is basically saying that the capability of Exascale will allow engineers to develop products that will improve people's lives, and also to get better and healthier products for the environment. So obviously, since they produce detergents and soaps and these sorts of things, environmental impact is important to them. So bringing this exascale capability is going to allow them to produce safer products for the environment and also better products for you and I. And so as we look to develop these new exascale machines, we had to focus on a variety of different areas. So one of the things we wanted to spend a lot of time with was around new software. And so I mentioned previously that we wanted to build machines that would provide more of a cloud-like experience. So a cloud-like experience means more converged workloads, more multi-tenancy. So being able to run, for example, HPC workloads and AI workloads on the same infrastructure. And it also allowed that general cloud experience of being able to create and destroy virtual clusters on demand for different workloads for different users. It also required us to look at some new compute paradigms as well. So as I mentioned earlier, there's a great diversity of processors, and we wanted users to be able to take advantage of them, whether they're more typical microprocessors or GPUs or FPGAs, or even some of the custom ASICs that are available out there, may be specifically tuned to do AI workloads. And we also reimagined the interconnect. So Slingshot, which is our interconnect that we've recently come out with, is specifically developed to accelerate HPC workloads. So from our long understanding of HPC and HPC workloads, we were able to make some specific improvements in some of the software on the Slingshot fabric to enhance the performance of the fabric and thus the entire system. And finally, we needed new storage because, as we talked about previously, the exascaler is going to both create a lot of data and use a lot of data. And we didn't want the storage itself to be the inhibitor of performance. And this included also intelligent data management to allow us to tier data and have it available in a variety of different types of capacities, performance levels, and also cost levels. And also, again, give efficient performance across the entire system. So let's do a deep dive, first. So this was Steve Conway from Hyperion Research. Hyperion Research does specific research into the HPC and AI markets. So Steve Conway felt that the investments that are being done through the exascale systems that are being built on behalf of the US government will advance the overall state of information technology. And that's exactly the goal we had, to produce technologies that could be more broadly used across not only technical computing, but also more traditional enterprise computing as well. So I talked a little bit about some of the software stack improvements that we made. And here is our software stack for these exascale computers as we go forward. So there's a couple choices here. One is a more traditional, so on the left-hand side in that light green or turquoise color, is a more traditional HPCM, what we call software recipe. So this is the type of management environment we have broadly across a lot of our, both Apollo and our supercomputing systems. So it's a more traditional type, hierarchical system management capability, and it builds on a lot of the typical components that you would see in an HPC software stack. So things like workload managers, such as Slurm and PBS Pro, for example. Also a variety of OS types, whether it's our own Cray OS, it's Red Hat with RHEL, and also others available as well. And finally, building upon the cluster manager itself, which again is a more hierarchical cluster manager. And finally, the Slingshot Fabric Manager, which actually manages and controls and monitors the Slingshot Fabric. Then finally, at the end, this is all built on a Redfish infrastructure on top of our hardware. Now, as a counterpoint to the more traditional software stack, we have what we call CSM, or Cray Software Management Environment, with a different software recipe, very similar to the one I just went through. Let me just highlight the differences there. Right now, we continue to support a variety of workflow controllers as well, such as Slurm and PBS Pro. But this is based upon Cray OS itself, because Cray OS has some capabilities that we can utilize as we develop this other type of software stack. It then has Cray System Management. Cray System Management, rather than being a traditional hierarchical type system manager, is actually based around microservices. So being able to spin up and spin down microservices as they're needed, this allows the scale that's needed in the size of systems we're talking about, and also gets us much closer to that cloud look and feel that we talked about earlier. Finally, again, Slingshot Fabric Manager is the way the Slingshot Fabric is both monitored and managed. And again, using Redfish as the interface to the hardware. So in summary, a couple of different types of software environments. On the left-hand side, the more traditional one with HPCM. On the right-hand side, more of a cloud-like type environment, allowing customers to enjoy that cloud experience. So first off, all of our Exascale computers are based upon the Cray EX supercomputer. So this is the densest and the most powerful supercomputer that HewlettPackard Enterprise produces. And it has up to 64 compute blades and up to 512 processors per rack. So a very highly dense type supercomputer. And it's also designed to be very flexible and to accommodate a variety of different types of processors and accelerators and technologies. And it's also future-proofed in the sense that we looked out in the future in terms of what types of processors, what types of accelerators might be available. What we saw was more powerful processors and GPUs, but also hotter and requiring more power to run. So we had to design our Cray EX to accommodate for those changes that we saw in the roadmap of a lot of the processor and GPU vendors over the next couple of years. We also wanted to be very green, so we wanted to supply 100% direct liquid cooling. So to be room neutral. So we had a lot of customers saying, I need a room neutral solution that doesn't add heat to my data center, and this is what the Cray EX does. And finally, in order to accomplish Exascale, it needed to scale to lots of cabinets. And this particular system will scale to hundreds of cabinets. And today, at Oak Ridge National Lab in Oak Ridge, Tennessee, we're putting together the first Exascale system, which is based around the Cray EX supercomputer. Now, in addition to the very optimized Cray EX that you see on the left-hand side here, very dense, liquid-cooled, room neutral, we also have a standard 19-inch rack type capability as well, with some of the elements that you see on the left, but again, in a more standard format type of environment. 19-inch racks with typically I/O in the back, probably disk drives in the front, standard type of switching, etc. And these types of what we call Cray supercomputers can also use some of the components that are from the left-hand side. For example, the software components, such as the Cray programming environment, or CPE, Cray OS, as well as Slingshot as the interconnect. So a great example of how we've taken some of that exascale technology that's being developed for the systems built around Cray EX and making them more broadly available for the marketplace. Now, obviously, the systems on the right don't quite have the capability of the Cray EX in terms of density and in terms of air cooling and efficiency. But they do share some of the capabilities as well. So again, taking some of that performance and features down into a different and more widely available format. So these are the 3 exascale computers we'll be building over the next couple of years. So the first one, as I mentioned before, is Frontier, and it's being built at Oak Ridge National Labs, as I mentioned, in Tennessee. It's a very large contract, as you can see on the screen here, and will achieve 1.5 exaflops of sustained performance. And it's built upon next generation AMD CPUs and GPUs. In addition to that, it has 700 petabytes of ClusterStor E1000 storage and will be used for both AI and HPC and converged workloads as well. After Frontier, Aurora at Argonne National Laboratory in Chicago, Illinois, will be deployed. And this was a partnership between us and Intel. And it will be built around Intel technology. So Intel processors and Intel Ponte Vecchio GPUs as well. It will also have the Slingshot interconnect, as with Frontier, and have Cray ClusterStor as some of the storage as well. And just like Frontier, will support both converged AI and HPC workloads. And then finally, the El Capitan system will be deployed in a couple years, and this will be at Lawrence Livermore National Lab in Livermore, California. And it will have more than 1.5 exaflops of performance with the latest processor and accelerator from AMD, as well as Slingshot as the interconnect. Again, ClusterStor storage will be part of the fast file system that's attached to this system. And again, it will support a mixed AI and HPC workload. So these are the 3 exascale systems from whence we're taking a lot of this new technology that I've been talking about. And so Rick Stevens, who is a part of Argonne National Lab, has said that these exascale computers are simply the biggest, baddest machines we can build on conventional technology. So again, we've used relatively conventional technology and taken it into a format to drive very high levels of performance. And so again, we wanted to focus these machines, as did the US Department of Energy, on not only leading science type applications, but also more practical applications that are very near us. And so an example of this was with the Japan's National Institutes of Genetics with their 5th generation supercomputer, where we took some of our technology and actually created some capability that the National Institute had not had before in order to do gene research for therapeutics as well as new pharmaceuticals. Now, another type of compute paradigm is what's available through our Superdome Flex family. So for those who have been familiar with the SGI ultraviolet system from a number of years ago, this is the latest generation of ultraviolet. We renamed it, we call it Superdome Flex, and we made it actually a bit more flexible, hence the name Flex, than the UV was. Now, for those workloads that take advantage of large shared memory, this is a perfect system for that type of workload. And it's very flexible because it can take a single module, as you can see on the left-hand side, which we call our Superdome Flex 280, and very easily add additional modules to increase the compute as well as the memory capability of the system. So it's a very plug-and-play type and grow-as-you-need type of environment. So again, this is high performance at scale, but at scale built around large shared memory. Now, again, one of the precepts that we had in developing our exascale systems was to be able to create technology that could be more widely used across a variety of markets. So we have a number of different types of solutions here that we provided. On the right-hand side, DZNE is a research institute in Germany that has been doing Alzheimer's research for a long period of time. And we actually used some of the Superdome Flex technology to speed up that research into Alzheimer's disease by up to 100 times by using in-memory analytics. So a great example of an application where by bringing all that data into a large shared memory system at one time, it allowed a large increase in terms of performance. In the middle, we work with Seagate, and Seagate was applying an AI algorithm that actually allowed them to detect flaws in the tiny integrated circuits in their hard disk drive controllers. Whereas in the past, it was very typical on a production line that you'd have a series of controllers going down the production line, and occasionally you would take one out and look at it to make sure that you were within process and it wasn't introducing flaws. But meanwhile, by the time you recognize that, you might have already had a number of different types of, or a number of flawed parts already going downstream and perhaps getting into disk drives and causing them to fail. So what Seagate did was to actually take some HP technology and take a picture of every controller going down the conveyor belt as it was produced, and it allowed them to specifically identify which parts were good and which parts were bad by comparing that photograph that it took with what should be a good controller. And then finally, on the left-hand side, as a part of real-time analysis, we worked with the Mercedes Petronas-based Formula One team to actually do real-time analytics in terms of how a race car is doing during a race, and allowing the crew and the driver to make infant changes as it went along the track and to make sure that car was performing. So that's an example of taking some of this technology and making it available in a real-time format. And so in this case, we were able to get 3x faster results by using some of this current technology that we're bringing out through our exascale machines. And so in a lot of cases, we're seeing redefined experiences as well as smarter operations. So I'll pick out a few of these as examples. So Centerpoint Energy is using our systems for doing incoming data processing from smart meters to understand what the particular load is from a power perspective across its networks. I talked about the Seagate example already, and also an example is a soccer stadium in the UK, right here on the left, where we're delivering real-time experiences to all the audience there at that event, and allowing them to not only see the game, but also enjoy ongoing analytics of the various teams of the game, maybe looking at other games going on and these sorts of things as well. So again, using some of this technology much more broadly across the industry. Now, to deep dive a little bit on storage, we found many HPC users were struggling with their legacy HPC storage. So typically it had a lot of I/O bottlenecks, some pipeline challenges, and it consumed too much of their budget. It was just too expensive at the sacrifice of their HPC budget. And there was a lot of frustrating finger pointing of various vendors that were not part of the same company that could actually tune the storage for the compute. So we actually came out with the Cray cluster store 1000, which is the storage that's a part of all our Exascale computers, which provides unprecedented scale and efficiency. And it has the benefits of using Lustre as an open source file system as well, so there's no license fees per terabyte that you might have in other types of disk solutions. At the same time, we provide enterprise-grade support through our HP PointNext customer support organization. And also, we built this solution in mind with our data management or DMF capability, which allows for tiered storage, which includes things like data protection, archiving, migration to further and further tiers of storage that are more cost-effective as you go further and further into the tiers. But with the overall appearance that it's actually local storage. And so in this way, we're able to transform the whole storage experience from a performance standpoint, from an integration standpoint with our supercomputers, and also from being essentially one vendor doing all parts of that particular solution for customers, both the compute and the storage. And so in this way, we've developed these types of technologies to prepare us for the exascale era. Again, to review new software that has converged workflows, multi-tenancy, new standards in manageability, microservices-based, for example, much more cloud experience. New compute technology, which allows a diversity of processors, data-intensive applications through our Superdome Flex type large system memory computer, and also we reimagined the interconnect through our HPE Cray Slingshot fabric, specifically optimized for HPC. We also have brought out new storage, intelligent data management through DMF version 7.0, which is our latest version of our data management framework, through our cluster store efficient performance solution that delivers unprecedented scalability. And again, to deep dive on our new high-speed interconnect that has high bandwidth, adaptive routing, congestion management, quality of service, and also Ethernet compatibility. So when you bring it into a typical enterprise data center, you can very quickly integrate that with standard Ethernet that's a part of that organization's internet backbone. So in conclusion, even though we've been developing the biggest, baddest supercomputers right now for the exascale era of the United States, we've been taking that technology and making it available much more broadly for a large group of users, for large different type of workloads, for green applications, for life sciences applications, in AI and HPC. So appreciate your time today and hope you have a good rest of the show. Thank you.